All right, so here's the screencast for single and double replacement chemical reaction. So in a single replacement, it's essentially that one single element is going to try to take the place of another element in a compound. So you're going to always have a free element and a compound. That's how you can tell these. And it's going to form a free element and a compound. The free element can either be a metal or a non-metal. So if it's a metal, it's going to try to take the place of the metal in the compound. If it's a non-metal, then it's going to try to take the place of the non-metal in the compound, and it like literally will kick it out by itself. So it is now going to come in and say, okay, I'm going to bond, or I'm going to take the place of B, and I'm going to kick B out by itself, and now I'm going to bond with C. Or if it's a non-metal, it will come in and it will bond. It'll kick out C, and then it'll bond with B. The main thing is that this won't always happen. You actually have to be stronger. You have to be more reactive or higher on the activity series chart to replace something else. So this is the activity series. So if you look at this, like lithium is the most reactive on this chart, going all the way down from lithium to gold. So lithium and rubidium and potassium and calcium are higher than these things down here. So you can replace anything below you. So manganese can replace zinc, but zinc can't replace manganese. So you can move down, but you can't move up. These guys down here are not strong enough or not reactive enough to kick these guys out. So you always have to make sure that these reactions are going to go. And it gives you this lovely chart. It also tells you for the the non-metals as well. So if A is a metal, you'll use the chart for the metals. And if A is a non-metal, you'll use the one for the halogens. So these are kind of your basic equations for these. It's always going to be a free element in a compound and a free element in a compound. So let's just do a few examples. So if I have copper, which is my free element, so it's a metal, trying to take the place or trying to join in this compound of silver nitrates, trying to break it apart. So copper is trying to, because it's a metal, it's going to try to kick out silver. It doesn't tell me a charge for copper. So I'm actually just going to make the assumption that it is a 1+ charge because now I'm going to have to form a new compound. So silver is now out by itself because if I look on the chart, copper is higher than silver. Copper is right here and silver is right here. So copper can replace silver. So silver's now out on its own, and the copper that is a 1+ is now going to bond to the nitrate that is a 1- and make the compound of copper nitrate. So you see how I have an element in a compound and then an element in a compound. And this ends up being balanced. In this case, I look at this and I go, zinc is a metal. So zinc is going to try to take the place of the metal in this compound of the tin. So I look on my chart, can zinc take the place of tin? And yes, zinc is higher. I know just because I know it, zinc is a 2+. And so I'm going to have tin out by itself. And zinc is now going to join with zinc that's a 2+ is now going to join with the chlorine that's a 1-, so I need 2 of those. And it ends up being balanced. They won't always work out this way. What if I had one where I had chlorine trying to take the place of fluorine in this compound? So chlorine is a non-metal. It's going to try to take the place of the non-metal. Chlorine actually cannot take the place of fluorine. Fluorine's higher on the chart. So I would literally just write no reaction. But the main thing is that one of the elements is going to kick out another one. If I had fluorine trying to take the place of chlorine, that can happen because fluorine is higher. So now fluorine is going to kick out chlorine. Chlorine is diatomic, so it's going to be Cl2. Hydrogen is a 1+ and fluorine is a 1-, so I'm going to form HF. And then I have to go back and balance this. If I have 2 fluorines on this side, I need 2 on this side. I have 2 chlorines, so I put a 2 there and now it's balanced. You are not necessarily going to have to figure out what the products are, but the main thing for you guys is just going to be able to identify them. So that's a single replacement reaction. Double replacement reactions are where you have a compound, or you have 2 compounds and you form 2 compounds. So 2 compounds in the reactants, 2 compounds in the products. So it's all going to be compounds. The way that I like to think about it is I like to think about the nonmetals or whatever is negative switching places. So I'm going to have this positive A bonded to this negative B, and this positive C bonded to a negative D, but now the negatives are going to switch places. So A is now going to bond with D, and B is now going to bond with C. In order for these things to occur, though, there's a few things that have to happen. Both of the reactants have to be aqueous. So in the examples that I'm giving you, both of the reactants are aqueous, meaning they're dissolved in water. So these are solids that have been dissolved in water. For these reactions to go, when I look at my products, one of the products must be a solid precipitate, meaning it's insoluble in water, so it's going to settle out of solution, and the other product must be soluble. So what you do essentially is you figure out your products, and then you look on the solubility chart. So it gives you a solubility chart where it tells you the positive that's bonded to a negative. So if I have ammonium bonded to anything, it's going to be soluble. If I have lithium bonded to anything, it's going to be soluble except this down here. So you have to check to make sure. So let's work through an example really quick. So PbNO3 plus Ki. I'm literally going to have these things switch places. Well, if the nitrate I know is a 1 minus, I have 2 of them, so the lead has to be a 2 plus. Potassium's a 1 plus, iodine's a 1 minus. So now I'm going to have iodine and lead bonded to each other. So PbI2.